It's not. She did something. Yeah, I just didn't.
This kind you're still be on track like Tuesday, Friday, multiple voice.
Yeah.
I think many of you guys have picked up packet 4 already, but if you haven't, you guys can come up and grab that as well. I think packet 4 already, it's just the one the short section. Okay, so let me just kind of go through the our calendar. We're in our final stretch here. So we're going to focus on multiple choice portion of fall semester. So derivative topics today. So today we're going to work through pages. Well, we'll start pages 1 through 4. I'll probably just pick out specific problems that I want to go over with you, and then whatever we don't finish will be part of your homework. So pages 1 through 4. And then on Monday, we'll work on, sorry, I meant to say page 5 through 8. So I'm more specific here. So pages 5 through 8, I did here. So page 5 through 8, 13 through 14. Those are good. That's the second half of first semester topics that I want to go over. And then your test part 1 is going to be Tuesday. And then the morning review, I don't have it all exactly in perfect order. So your fall semester topics are page 1 through 4, 5 through 8, 13 through 14. And then your morning review is page 15 through 18. So if you guys can just make a note of that in your packet. And then the rest of the pages are for second semester topics. So page 9 through 12, 19 through 22, and then the morning review is inside there as well. And then the multiple choice 9 through 16 will be next Friday. On the test, you're going to see a mixture of calculator and non-calculator questions, and I'll specify on the test what's meant to be calculator so that you don't have to show your work, you can just provide the answer. But most problems, I'm going to ask you to show your process, show your work. If it's a product rule, chain rule, implicit, I'm going to ask you to show all your work for to earn full credit. But it also means that if you mess up on multiple choice question, that you can still earn partial credit because you're showing your steps. Okay, so next up, I want to go over the formula sheet. You won't get to use this on the test, but I just wanted to have a way for you to kind of access all the information that we've learned in an easy place. So I put together a formula sheet so that we can do that. And I didn't quite organize everything like first semester together and second semester together. They're sort of like that, but most of the first page is first semester. So I kind of highlighted all the ones. Basically, the everything in the top half is first semester. And then it's just the very bottom portion that's not. Once we start with the integrals, then it's not. So if you just want to make a note of that. The second page is more of a mixture of first and second semester topics. So, but if you can, and then you can pick up the formula sheet too. I think you may have that packet already, Jackson, but. And then second page has more of a mixture. So second page, there is under particle motion. These are all first semester topics. It's just, that average velocity is just slope of position. Average acceleration is the slope of velocity. Displacement, well, sorry, accidentally, this is our second semester here. That's okay. You guys already know these formulas. And then increase, decreasing speed. And then finally, at the very bottom of the page, all the miscellaneous topics below are also first semester topics. So being able to find derivative inverse set of points, log differentiation, log properties, and second derivative test. Okay, moving on to our packets. Oh, sorry. Let me just kind of. So the rest of the packets has just formulas. This is the formula sheet that you guys were that I graded as a quiz. So this has all the formulas first and second semester in terms of derivative and integral rules, and then I also included a worksheet with formulas for just kind of miscellaneous first and second semester topics that are not quite derivative integral rules. A lot of theorems that I put here, so it's good to kind of look through. And then in the back, I have a blank worksheet in case you want to practice as we move closer towards our AP exam. And then I also have a blank worksheet for all the theorems in case you want to practice writing out all the theorems. So I have the keys to begin with, and then the blank copies with the worksheets if you want to have a chance to practice through all the major formulas that we've learned. Okay. All right, moving on to packet 1. Packet 4, page 1. So your multiple choice questions 1 through 8 are going to come from these topics here, which these are all the topics, but 1 through 11 are first semester topics, and then 12 through 16 are second semester topics. So I'm just highlighting the first semester topics for now. So limits and continuity, L'Hopital's rule, product rule, chain rule, quotient rule, implicit differentiation, theorems such as EVT, mean value theorem and rules, related rates, being able to interpret a derivative graph, using first derivative test for concavity, second derivative test to find relative max, relative min, points of inflection, concave up, concave down intervals, particle motion, position, velocity, acceleration, trig, natural log derivatives, derivative of inverse at a point, and then linear approximation. So I think a lot of these topics, hopefully we feel pretty good on because we've seen them kind of popping up in our FRQs. All right, so I'm going to do probably most of the first page, and then we'll kind of jump around after that. So let's start with number 1. It says the graph of f is shown above, at which value is the graph continuous but not differentiable. So continuous means it needs to be part of a connected graph, but not differentiable means it's not a smooth point. So if we look at our options here, B is not continuous, so this one is definitely out. C that's part of a smooth curve, so it's continuous and differentiable. That one we don't want to use. D is not continuous, so that doesn't fulfill. E is continuous and differentiable because this is part of a smooth curve. Answer choice A is continuous, no breaks, no holes, but it's not differentiable because it's not part of a smooth curve. So option A. Number 2, we have a piecewise function. Which of the following statements are true? You have all these, you see the word, whenever I see the word continuity, I'm always thinking, okay, I know I can step through continuity conditions and this should be able to answer a lot of questions for me. So I'm just going to step through my continuity conditions. So my first condition is, does my point exist? And then you're always going to be told the focus of the problem here. We're focused on 2 here. So I'm going to say f of 2 is equal to 7. So the point exists. That one is safe. Second condition, does the limit exist? The limit is talking about, is the graph approaching the same y value from both sides? This is just a point. We're not going to do anything with limits with this one. The graph is here because the x doesn't equal to 2 means that to the left of 2, to the right of 2, it's all contained within this function. So if we want to find the limit, we want to find the limit of the graph, not the point. This is just a point. The point has no say as to what the limit of the graph is involved with. So x approaching 2. Anytime we see a limit problem, our first step is always just direct substitution. So we plug 2 in for x, get 8 minus 6 minus 2, which is 0. We get 0 over 0. So we can go through factoring, but I think most of us prefer L'Hopital's rule. It's quicker, a little faster. So L'Hopital's rule says take the derivative of the top, hit the derivative of the bottom. 4x minus 3 is the derivative of each of these terms. X minus 2's derivative is 1. We reevaluate our limit. We should get something other than 0 over 0. We get 8 minus 3, which is 5. 5 over 1 is 5. So the limit exists at 5. So it passes. And now the third condition, we're not creating anything new with the third condition. We're just going back and asking, are these in agreement? And we see that these are not in agreement, right? The order pair is at 7, but the limit is going towards a different location, right? 7 and 5 are not in agreement. So it fails the third condition. So the graph may look something like this. Right. The order pair is sitting up here at 7, but the limit is headed towards a different y value. Now, if you look at this, we can go through our conditions here and see which one is best fit. Okay, continuous at x equals 2, obviously not true. If it's continuous, it would have to pass all three conditions. There's a removable discontinuity at x equals 2, so that means there's a hole in the graph, and that is true. Right? We definitely see that there's a hole in the graph. Removable discontinuity means it passes the second one, but not the third. So this one is our best option. The other ones are not correct because jump discontinuity would mean that the limit does not exist, but we can definitely see that the limit does exist. So third condition, part C is wrong. And then discontinuity due to a vertical asymptote. These are both kind of talking about the same thing, which these are both not true. Number 3, limit as x approaches 2 equals. So here we definitely have to involve both of these piecewise functions because we have to the left of 2 is a natural log of x. The right of 2 is different one. So we're going to do a one-sided limit and basically doing what the arrows are doing graphically. Are the arrows moving towards the same y value? So we'll do limit as we approach 2 from the left. And that is clearly the natural log of x. We'll do that. And then separately, we'll do limit as x approaches 2 from the right side of 2, and that is referring to the x squared natural log of x. Now, these are just notations. This is telling us where we're coming from, but we always do direct substitution. Remember, we don't do anything with decimals unless we see something. After direct substitution, if we get like undefined, then we can play with decimals, but we never play with decimals to begin with. We always just do the full value. So if I plug 2 in, I get natural log of 2. If I plug 2 in here, I get 4 natural log of 2. And these are obviously not the same y value. So one side is headed towards natural log of 2. The other side is headed towards 4 natural log of 2. And they are not in agreement. So therefore, the limit does not exist. Number 4, limit problem. First thing we do is always direct substitution. So go ahead and try that. See if you can plug in pi, see what you get, and from there, decide what could be a good option based off of what you get back in return. Remember, if your limit after direct substitution gives you a real number, then there's no need to do anything else. You've reached your solution. But if you get something other than a real number, then we got to make a decision. Do we keep going? Do we say the limit doesn't exist? Okay. So I am getting 0 over 0. So that gives me ability to know, okay, we can definitely, I mean, this is kind of in the holding pattern here. We don't really know what the limit is, but we do know that we have to keep going. We can't say that limit doesn't exist. The limit does exist. We just are not able to see it right now. So this is definitely a good candidate for L'Hopital's rule. So let's do that. Cosine of pi, its derivative is, sorry, cosine of x, derivative is negative sine of x. Sine of u's derivative is cosine of u times u prime. The 1 goes to 0. X squared becomes 2x. And then pi squared. Remember, this doesn't go to 2 pi, right? This goes to 0 because that's a constant. So now that you have your derivative version of your expression, reevaluate your limit, and hopefully this will get us down to a real number. Sine of pi is 0. Cosine of 2 pi is 1. 1 times 2 is 2. And 2 over 2 pi, the 2's cancel out. Pi is in the denominator. That's left over, so 1 over pi is our answer. By the way, you also have a key attached to this packet, so you can always check your progress if you're working ahead of me. Okay, page 2, number 5. This is now limit as x approaches infinity. We know that if we're approaching infinity, we have a different set of rules, right? We don't compare, we don't plug values in, but rather we compare degrees. So I have that on near the top of the formula sheet here, that if we're evaluating limits approaching infinity, we compare degrees. If our denominator is greater, then our limit is always 0. If our numerator and denominator have the same degree, then it's the ratio of the coefficients. And if the numerator is greater than my denominator, then the limit doesn't exist. So if we look at number 5 here, we're approaching infinity, and we're going to compare degrees. But overall, what's the degree of the numerator? What's the degree there? Is it degree 4? X squared, yeah. Square root of x to the 4th becomes x squared. So technically, these are sitting at the same level. So because of that, even though it looks like the numerator has a higher degree, overall the degrees are the same. So we just take the ratio of the coefficients. So the coefficient of my first term of my numerator is √9, and the bottom is 1. So my ratio is just √9 over 1, which is 3. Number 6, limit as x approaches a. A is a real number, so think of a as like a number, like 2 or 3, right? Imagine this is limit as x approaches 2 or limit as x approaches 3. What would you do? You would plug in that 2 or 3, right? So same thing here. We're just going to plug in a in for x and see what we get, right? So let's plug in a in for x. We get 0 over 0. That gives us the ability to find the limit. Use L'Hopital's rule. So we can find the derivative of each of these terms. Remember, a is a number, so all these will go to 0, but x becomes 1. X cubed minus a cubed, we get 3x squared minus 0. Plug in a in for x, we get 1 over 3a squared. And that's as far as we can go. Okay, number 7. We have f of x equals x cubed or cube root of x. Now we're moving on to just finding straightforward derivatives here. You may be thinking, wait, maybe I got to go through quotient rule here. Remember, we only do quotient rule if we have multiple terms in the denominator, right? We know that there's an easier or there's a more preferred path. If there's a single term in the denominator, we should just bring it up and rely on power rule. So this is kind of disguising itself as quotient rule, but really we should be thinking power rule here. So, but if we don't do power rule, we do have to do some cleanup. So I'm going to rewrite that denominator as a rational exponent. And I'm going to bring the x up to the numerator and merge them together and see if I can get it to be one term before I go through power rule. Now you could go through quotient rule and product rule depending on where they are, but it's going to make it messier than you would like. So I think the preferred path is let's go through power rule, but power rule only after we've merged them together. So if I'm trying to multiply bases, I'm going to be adding exponents, right? So 3 minus 1/3. It's going to be the same thing as 9/3 minus 1/3, which is 8/3. So we can just find the derivative at this stage, right? X to the 8/3. So y prime is equal to power rule. Subtract 1 from the exponent. And that's just equal to 8/3 times the cube root of x to the 5th, which if we try to keep going here, for every 3 x's, we can pull 1 out. So if we pull 3 out, there's still 2 left over inside. So 8/3 x times the cube root of x squared. Okay, page number 8. Let f and g be differentiable functions with the following properties. G of x is greater than 0 for all x, so we know that g of x is always positive. F of 0 is equal to 1. We know that h of x is equal to f of x times g of x, but then h prime is f times g prime, then f of x is equal to. Now, this may not feel like that it's connected here. Like, how did this get to that, right? I mean, if we were starting with this, and if I asked you to find the derivative, what would your first instinct be? Product rule. So how is it that our product rule, this doesn't look like product rule, right? This looks like maybe a portion of the product rule. So maybe there's something along the way that got reduced down to this, right? So let's do this. Let's see if we can find that bridge. How did the derivative of this using product rule get to this? So let's build out using product rule and then compare, how do we get from what we know to be true to this stage? Okay, so let's build out our own derivative and compare it with how they got to their result. So product rule, f prime g plus f g prime. So they're saying that this derivative is going to reduce down to that. So do you see something in this derivative that looks like this? What looks like this? The second term, right? Fg prime. So how is it that this is not there? What could cause this to disappear? Right, if maybe one is a constant, or maybe if one zeroes out, right? Maybe this zeroed out, and so they didn't need to include it. So they, if anything zeroes out, we don't include it in our answer. So maybe something here is zeroing out. So let's see if we can continue our work here. So could f prime be the thing that's zeroing out? We know that f of 0 is equal to 1. G is always positive. So we know this can't be zeroing out, right? G of x can't be the culprit because it's always positive. So this is not 0. So must be f prime that's 0, right? F prime is what's equal, must be 0. So if f of 0 is equal to 1 and the derivative at that point is 0, then f of 0, the f of x must be equal to 1, right? Because f of x is equal to 1, that makes that a true statement. F of 0 is 1, but f of x must also be a constant. That's the only way that the derivative can force it to be 0, and that's causing it to zero out. So then f of x must be equal to 1. So we're kind of having to kind of look at what we have versus how they get there, and then kind of narrow down, okay, process of elimination to try to find our solution. Okay, I think number 9 is a bit more straightforward here. Let f be a differentiable function. F of 2 equals 3, f prime of 2 equals -5. We have g of x equals f of x, which of the following is an equation of tangent line. So we're just going to build our tangent line, find our order pair, find our slope, point slope form. But we're not finding the derivative. We're not finding the equation tangent line of f. We're trying to find the equation of tangent line for g, and g is built this way. So let's find the order pair of g. Let's find the derivative of g. and then build our tangent line. So we can't build tangent line at this level because this is F. We want tangent line for G. So let's find the order pair first. F of 2 is 3. So we have our order pair. Now to find our derivative, we need to find G prime. But to get to G prime, what are they trying to get us to use here? Product rule, yeah. I can't just say 1 times F prime. We got to go through the product rule here. So F prime G plus F G prime. So for X, we can go through power rule. For F, we got to leave it in function notation. F prime G plus F G prime. Replace every X with 2. Get it down to our slope value, and then put it into point slope form. Page 3, let's go to number 11. Okay, so number 11, the figure shows the graph of function G. And the line tangent through the graph at x equals -1. Let h be the function defined by h equals e of x times g of x. What is the value of h prime of -1? So if I want to find h prime -1, I got to find h prime of x. To find h prime of x, hopefully we can recognize this. Oh, I got to go through product rule again because I have 2 separate expressions here, 2 separate terms being multiplied. So let's build out our derivative using product rule. So f prime times g. We know e to the x's derivative will stay as e to the x plus f g prime. Okay, so now that we have our derivative, replace every x with -1 because that's our goal. We're trying to find h prime of -1. So e to -1, we figured that out. I mean, those are numbers. The only thing that that we have to kind of get it in, because we know that all our answers are out of function notation here. So we have 2 things left to figure out. We need to find g of -1, and we need to find g prime of -1. So g of -1, that should be easy. G of -1, this is the graph of g here. So we know g of -1 is 3. That's just the order pair. So that's an easy one to find. But then it's also asking for g prime of -1, which is the slope of this curve at that point. Now, we don't have a function, we don't have a g function to find the derivative, but we do have this line here. We know this is the tangent line. So that tangent line is helpful because we know that tangent line is sharing the same slope as the curve at that point. So if I can figure out the slope of this line, then I also have the slope of the curve at that point. So then the slope of the line is just change in y over change in x. So -3 minus 3 over 0 minus -1. I get -6 over 1, which is -6. So the slope of this line is -6. You can also do rise over run. You can count down 6 over 1. And so that's our slope. Slope of the line is same as slope of the curve because they're tangent to each other. So I have e to the -1 plus, so 3e to the -1 minus 6e to the -1. So that gives me -3e to the -1. Now, if I want to get it into this form here, I can just push that e down to the denominator because it has that negative exponent. So -3 over e. Uh, 12 and 13 are calculator questions. I think I want to leave for you guys to do these on your own for homework because a lot of these problems are just find the derivative, find a way to, you're basically looking for a critical point, but the critical point is hard to find algebraically. So you're just graphing that derivative and seeing where it crosses the x-axis. So that's a lot of times your calculator active problems are using the calculator to solve a solution that's otherwise difficult to do. So graphing something and putting it, looking for the x-intercept. So you guys can try that, but then you can also check with the key a little bit later. So with the remaining time, I just want to kind of highlight a few more problems here. So page 4, let's look at 14. This is like a popular type of AP multiple choice question, number 14 here. We have a piecewise function. It says, let the function be defined above where C and D are constant. So we'll treat C and D like numbers. So pretend C and D are like 3 or 4 or 2 or 5. F is differentiable. So that's something that they're trying to, that we're going to have to make sure we understand. So smooth curve. What is the value of C plus D? So we have a piecewise function here. Piecewise function means that they're potentially separated, but they're telling us that the graph is differentiable, meaning that these two piecewise functions are not only going to connect at 2, it's also going to connect in a way where it's a smooth transition. There's not going to be a sharp turn. So this type of problem is where we want to have to take advantage of 2 separate equations. We are missing 2 unknowns, so we need 2 separate equations. So one equation is the continuity portion. If it's differentiable, it's got to be connected and it's got to be sharing the same slope. So if the graph is continuous, that means these 2 functions must meet at x equals 2. That means I can set the functions equal to each other. So I can do this. I can say cx plus d is equal to x squared minus cx. And we know every x is at 2. They must be meeting at 2. I can replace 2 in for x. So I get 2c plus d is equal to 2 squared, which is 4, minus 2c. I'll come back to that because right now I still don't know what c and d are. But we also have a differentiable portion, which is talking about the derivative. So we can also set the derivatives equal to each other. Because if it's differentiable, that means these two graphs are going to be sharing the same slope. And if they share the same slope, that means that's at the derivative level. So we can find each derivative of each of the terms and set them equal to each other. Okay, what's the derivative of cx? Imagine this is 2x. What's the derivative of cx? Just c. What's the derivative of d? Good. It's like 3x plus 4, right? If it's 3x plus 4, your derivative will be 3 plus 0. Cx plus d, it'll just be c plus 0. Okay. All right, derivative. What's x squared's derivative? 2x minus c. And we know this is also at x equals 2. So if I plug 2 in for x, now we should be home free here. So get c is equal to 4 plus c. Sorry, minus c. And then the c's can come over. We can, because we're just ultimately trying to find c and d. So we get 2c is equal to 4, divide by 2, so c must be equal to 2. And if I have this, I should be able to go back to my first equation and figure out what my c value is, or what my c plus d value is. So if I combine this, I get 4c plus d is equal to 4. Plug 2 in for c, I get 8 plus d is equal to 4. So I get d is equal to -4. Thank you. Oh, he's not here today. So my d is -4, my c is 2. So then c plus d will just be -4 plus 2, which is -2. Let's finish off with 19, bottom of the page here. What is the slope of the line tangent to the curve 3y squared minus 2x squared equals 6 minus 2xy? We want to find the derivative. A lot of these are power rule, but we see a couple things sticking out. One is there's a bunch of y's that feel out of place. So that's going to have to involve implicit. And then we also have, there's a hidden product rule here because 2xy, x and y are being multiplied. So there's also, we're going to find the derivative and then plug in 3 and 2 for x and y, and then try to solve for dy dx. Remember, with implicit, we go through our derivative process the same. It's just that when we come across y's derivative, we have to attach that dy dx. I see 2 y variables, so I should be expecting 2 dy dx's that pop up along the way. I'm protecting my entire expression with a set of parentheses because I know that this minus is going to end up distributing through the result of my product rule. So I know I got to solve for dy dx, but I'm going to save a little bit of time here. I'm going to replace every x and y with 2 and 3, 3 and 2, and then see, and then just try to get my dy dx solved. So I'm going to just, rather than having to move everything, keep track of all the variables, a lot of things will cancel out if I just go ahead and replace all my x's and y's with 3 and 2. Because I'm already at the derivative level. I already have my unknown variables identified. Combine like terms together, 12 minus 6 is 6. Negative 4 plus 12 is 8. Oops, I think I messed up along the way here. Oh, I forgot to distribute the negative through. So this should be minus. Sorry, it should end up being 8 over 18 or 4 over 9. Okay, so your homework is to finish pages 1 through 4. I'll send out a reminder over the weekend, and also send out a reminder what pages to focus on. This Monday, we'll focus on the rest of the pages, and then morning review Tuesday, the preparation for Tuesday, part 1 of our multiple choice test. All right, come get your phones.